time. Hello, starting the recording. Okay. So here's an example of a link, a list, right? Okay, so this example is kind of misplaced because what Python calls list, right, is actually a dynamic array. Okay, so basically, when you use the brackets, like creating an enumeration of elements as a list in Python, internally, it's basically the elements will be side by side. So it's the compromise, right? The array list is basically a compromise between the advantage of an array, right, for fast indexing, but with the dynamics of a linked list. So the compromise is an array list, or a dynamic array, which gives you side by side, but if you need to append more elements and you don't have the capacity, the data structure will grow in order to accommodate more elements. So just keep in mind that Python, what Python calls list, is not a linked list. Okay, it's a dynamic array, probably implemented typically like an array list in Java. Okay? When we talk about lists, we also need to talk about an important way to build lists, or let's put a collection of elements, which is called list comprehension. List comprehension is, very popular in many modern programming languages, right? You have this ability to build lists. And you're going to see that, of course, you see that in Python, but you also see in many other programming languages. For example, in functional programming, we're going to discuss Haskell. Haskell has a mechanism for list comprehension as well. So very popular in functional programming. So the idea is that you're going to define an expression that is going to be used to add elements in this list that you're going to build. And basically, you're going to use another collection to build this collection, this list here. So basically, you're iterating through this list, and you're going to check. Optionally, you can check some condition, and then this iterate var, this variable here, can be used in this expression to build something different. All right, so remember we have the fruits, three fruits here, and I want to build a list with the length of the fruits, but only if the length is greater than 5. I wasn't very creative when I was doing this slide, but basically we're looking through the fruits list, right? And at each iteration, fruit is the temporary variable that will hold the value of each individual fruit. So start with orange, and then the test condition will check. We're only gonna use this fruit if it passes this test condition, which is checking the size of that string. So this string here has 6, 6 is greater than 5, test the test. So this is the expression we're going to execute. Length of fruit is 6. 6 is what we're going to add in this list that we're trying to generate. The other one, banana, is also 6, but this one, apple, is 5. 5 is not greater than 5, so that's why we don't see 5 here. And if we were to do that in Java, this is not doing the same. It's basically showing a linked list in Java and indexing and looping through using an iterator. Okay, so that's what you have to be careful. Arrays or lists, don't be misguided by the names used by programming language. What Python calls list is technically a dynamic array, similar to Java's array list. If you actually want to use a linked list in Python, you have to use the DQ class. I believe it's a class. Okay. So moving forward, I know it's a lot of content today, and because this is more theoretical, I don't have an activity. It's more like information. We also want to discuss records. Although we don't see records, although Go, the Go programming language, reintroduced records, the struct type. We're going to see later in this course. But records, you can think of records as the first, like the first implementation of constructs that preceded classes, right? So records are very similar to classes. The only difference is that we don't have the methods in a record, but we have all the data structure that we see in a class when you define variables, right? You see that in a record. So it's an aggregate of data elements in which the individual elements are identified by names and accessed through offsets from the beginning of the structure.
So aren't they usually like final? Is that? So
Well,
you have nothing to update them. You don't have methods to update them.
When you talk about files, you're thinking about storage, right?
I meant final.
Oh, final?
Yeah, like you can't change them. You access it.
No. Final is like when you want to say that the class cannot be specialized. You put final, right? Records they're basically a mechanisms to allow you to define new data types. It's to build data types just like classes.
I think the word I was looking for was constant. So, never mind. You answered my question.
Okay, so this is how a struct or a record looks like. I'm creating a struct for a student. It's basically a record that defines what is a student. So we specify that a student has an ID and a name. But look, so this really looks like a class, right? But you don't define functions or methods within the struct. That's the difference, right? But this was available since C, right? So C had the struct. And as I said, having a comeback in Go, later you're going to see that Go is reusing the struct to create those, the ability to create those types, okay? So here I'm defining 3. So once I define the structure, I can use as a type to declare variables. So S1, S2, and S3 are of struct student type. Then I can, just like we do with object-oriented language like Java, we use the dot operator. So S1, I want to access the ID field within S1. So I know I have S1.ID, so the dot operator, to get those to those individual fields, just like we do in Java, for example. So another type, so we can cover all the data types or data or constructs available in programming language. We have the tuple, right? So the tuples are very similar to records, like structs, for example, record structs. The only difference is that they are not named, okay? So it's more like the individual fields are based on the position. So the tuple has an order. So the first tuple element, I'm going to say it's the ID. The second one is going to be the name. So that's how I can use that similarly to records, because I can have different types for the tuple individual elements. So I'm mixing integer with strings here in this tuple. Right? So what else? Tuples, I believe in Python, they are they, can we change a tuple once we define? You can check that. I have an impression that a tuple are read-only, but you guys can check that, Google that to confirm. But that also varies from programming language to programming.
So we were doing a priority queue in implementation of tuples in algorithms class, and it's either destroying the old tuple and putting a new one in there, or it's updatable, because
so they are
the first index in your tuple is what you prioritize by in a priority queue.
Okay, and that's in Python? Mm-hmm. Okay, so never mind then. So this is interesting when you look through an array, and because each of the elements of this array is a tuple containing two values, you can individually get the elements by enumerating variables here. I think that's pretty cool. It's very common too. Now let's move to pointers and references. You don't see support for pointers anymore, although you still, of course, see support for references. So let's talk about pointers first. So when you define a pointer, the value of a pointer is a memory address. This is essentially what a pointer is. Okay. And you use special values, usually new or null, to when you want to assign. You can't assign a specific address to your pointer. Then we say that it's null, right? Because it's not pointing to any specific address. So you can use that to check if a pointer is not initialized or not by checking if the pointer is null. Programming language that use pointers, they usually consider null as false. So you could use something like if not the pointer, means that if the pointer is not initialized, so you can use that in an if condition. And when you use a pointer, basically you have two operations that you can perform. One is assignment. So assignment sets a pointer variable value to some address. You have this operation called dereferencing. So dereferencing a pointer retrieves the value of the entity that the pointer is referencing to. So what does that mean? Find the preset. Oh, I guess this one. There we go.
That's
There,
a
preset.
There work.
I thought we were getting somewhere, and then it just kept
Preset
going.
7 and 8.
Hi, Nick.
What are you doing, Nick?
Gotta be it.
Time to use
Yeah. We should make it so the presets are like per instructor, so you come in and log in and you have your own presets.
That'd be an extra $100,000.
You're not wrong.
This is one address. Let's say this is another one.
Everybody just pays an extra $700.
You have the value 10 here. You have the value 32 here. Okay, and then I'm gonna say E is a pointer, and I'm going to assign a value. Say 00 FF So I assign the address. So pointers allow you to directly reference memory, right? So I want to address this specific memory location. So I use a pointer to assign a memory address to that specific memory location, right? Usually we don't do that, but for some applications, that's important, right? So let's say you're writing the low-level code to control a satellite hardware, right? Something very specific, or even some Arduino programming. Like, do you guys do Arduino or Raspberry Pi controlling some external hardware? So you probably did some application that require you to set a specific value to a port or a specific address to get that LED light up, right? Something like that. So programming language that allow you to address memory directly, they're very good for those type of applications, right? Of course, we will write this low-level code only once, and then we build an interface, a higher-level interface, so other programs can use our interface to do all these operations, but not necessarily every time having to figure out what's the memory address that I need to set. No, create a higher level function that sets what needs to be set, but making function calls something higher level, right? So you build a higher level interface, but at some point you need to make this low level settings, right? So for low level type of programming, hardware controlling, this is very useful. So specifically, we're going to use C as the example this is how you declare a pointer. So you use this symbol, this splash symbol, to declare that the variable is a pointer for integer types. So this value here, this memory location here, is gonna have an integer. So that's important to declare a pointer as of specific type, because you may want to do pointer arithmetic. Like if I want to move to the next address, I have to skip, let's say an integer is 4 bytes. So if I want to move to the next, so if I want to do P++, that's pointer arithmetic. Because I know that the integer is 4 bytes, it will automatically move to the next address, right? It will skip, because this value 4 bytes is to hold this integer. My pointer is of an integer, so if I skip, if I do P++, the implementation knows to skip 4 bytes. If this pointer was char, which is 1 byte, if I did P++, instead of skipping 4 bytes, it will skip 1 byte, because it knows that the char is just 1 byte. Does that make sense? Okay. So if I do something like print P, P is a pointer, it will print the address. Okay. But what if I'm not interested in the address itself? What if I'm interested in the actual value that is stored in that address? So that's dereferencing. So if I do asterisk P, I'm dereferencing the pointer. So give me the value that is stored at the address pointed by my pointer variable. Okay, so that's what dereferencing means. So here's an example. So in C++. Okay, so remember we had that student struct. So I'm declaring S as a student type, struct student type, and I'm assigning 1 to ID and John to name. Then I'm going to create a pointer of struct student. Okay, and I want that pointer variable to point to that object, to that struct. Right? So this is the ampersand symbol in this context is basically saying what's the address of variable S? What's the L value? Remember L value? L value refers to the address of a variable, right? So the left side of the assignment is L value. So what is the L value? What is the address of S? Save that into P. So P now points to that struct, that record. So if I want to show the address of S, I can do that using P, because P, the value of P is a pointer variable, is the address of S. Now, if I want to retrieve information associated with this S struct, including the ID and name, but instead of using the S variable, I want to use P. So I need to dereference P. Okay, so I'm going to use splash P, so that I'm dereferencing P. Once I dereference P, I'm basically accessing the same record, right? Because P, remember, P was pointing to S, this struct here. So if I do ID, I'm going to see 1, and if I dereference P and call name, I'm going to see John. You guys understand this example? Okay, so that's dereferencing. So basically, this pointer allows me a different way to get to that record. Another way to do that, instead of dereferencing, is using this operator here. If I use pointer and use this kind of an arrow, this has an implicit dereferencing happening. But it has the same effect. So pointers give the programmers a lot of flexibility, but must be used with great care to avoid not two, right? I made a mistake. Two potential problems. Dangling pointers and memory leaks. So let's talk about these two problems. So dangling pointers. So a pointer that contains the address of a variable that has been deallocated. Okay. So they're harmful because they can be used to reference something completely different and to intentionally modify other data areas. Okay. So let's say this example here, we started by, say, int x is n, and you're using the address of x, right? And, well, this variable was probably stack allocated. That's not a big deal. But let's say when I'm dereferencing this variable, I'm thinking that I'm changing this variable x, right? But let's say for some reason this variable becomes out of scope, so this variable doesn't exist anymore, and I try to dereference the pointer thinking that I'm still accessing variable x, but I'm not, right? The variable was out of scope, it was terminated, right? So I'm thinking that I'm accessing that location, but I'm not, okay? So that is a situation that can cause harm. Okay, so essentially a dangling pointer is a pointer that is referenced to a memory location that is not the location that I'm expecting, or I'm thinking that that's the location that I'm using, right? Let's see if I can come up with a better example. This makes more sense when you do dynamic memory allocation. Let's say that struct student S was dynamically allocated. New student, let's say, and go, right? And I got the address of S. I'm thinking that I'm changing the ID of S to 20, but at some point here, I decided to free this dynamically allocated memory. Usually we use delete to free the memory. So the memory was free, right? So I free the memory, right? So this area is not allocated the heap. It doesn't refer to that struct that was allocated anymore, but I'm still thinking using P. I'm still trying to make changes on that struct that it's not there anymore, right? So that's a dangling pointer. It's a pointer that doesn't refer to some object or something that was allocated and is currently valid. Okay? And if you try to modify something like change the ID, but that area is not allocated, the program will crash. Okay? So that doesn't work. If you try to, in your program, if you try to access an area that is not allocated anymore from the heap, it was free. So that area might be being used by some other program, right? So it creates problems, and the operating system has mechanisms to protect or to avoid one program accessing area reserved to another program, right? So your program will most likely crash. And the other problem is memory leak. So memory leak happens when a pointer is assigned to a new value before the previous allocated area is freed. Okay, so basically you have a pointer that, for example, is associated with the student, right? And that's the only way for you to get to that student, right? So say you created this guy, P, referencing this student, right? And then later, right, what you should have done was doing delete P to free this area that you allocated. But you didn't do that. And what you did was you allocated some other student. Okay? But you didn't free that area before you do that. So that area is still allocated. So if you keep doing that, you eventually you're gonna run out of memory because you keep allocating, but you're not freeing the memory. Okay, so those are the two problems. First is dangly pointers. Pointer is a pointer that is referencing an area that shouldn't be referencing. It might be an area that refers to an area reserved to another program or something that your program shouldn't have access to. And memory leaks, you keep allocating, but you're not freeing the memory. You're going to end up having memory leak. You're losing memory because you're not freeing the memory. You're allocating, but you're not properly freeing the memory. Then we have references, very similar to pointers, but without all the problems that I mentioned about pointers. Okay, so references are much safer. First of all, you cannot arbitrarily assign a memory to a reference variable. Okay, so you can't do things like I did in the beginning. P receives some memory address. P is a reference variable. Doesn't work. You can only assign objects to references. So it's safer. Here's an example of a reference. So the way you declare a reference in C++, for example, so C++ is used in the examples here because it supports pointers and references. So it supports both. So instead of using the splash to declare a pointer, you use the ampersand. So as you can see, why C++ is hard? Because there's a constant reuse of symbols, the same symbols with different semantics, right? The ampersand symbol can be used as to retrieve the address of a object or a variable, but can also be used to declare a reference. So that's two different semantics for the same symbol. The splash symbol also has different semantics. It can be used to declare a pointer, but it can also be used to dereference a pointer. So different semantics, same symbol. That adds confusion to the language. So here, the ampersand symbol, because it's on the left side of this, you're declaring this variable here, you use the semantics is this is a reference variable. Okay, so look at that. You assign S, and they didn't put the ampersand on the right side, right? So it's implicit that you're gonna get the address of S, but you don't have to explicitly put the ampersand. That would be too confusing. The syntax is confusing. But what are we doing here is very similar to what we did with splash P receives ampersand S. The difference is that P is not a pointer, it's a reference. Okay? And you can use P just like you use S. You don't need to dereference. So a reference variable, you don't have to dereference to get the value. You just use as you use S, right? It's the same. You see, I don't need to put the splash here to dereference P. P is a reference. I can treat a reference variable as an alias to S. This P here is an alias to S. I can use the same way I use S, I use P. But just keep in mind, if I use P to modify the name, for example, S will be, because they essentially pointing to the same object, they will be, you can use S to see the changes made in name. Okay, so in summary here, references are a preferable mechanism compared to pointers because they're much safer. You don't have all this freedom like we have in pointers. Like allow you to arbitrarily reference a specific memory address. You can't do that with references, right? Although you can have a reference point to another object, but the mechanism, it becomes pretty much like an alias to that variable. Yes?
With this example, if you did the same thing without the ampersand, would it be the same thing?
So you're not doing P, you're just assigning S to P. I think it's going to be different. So you're making a copy, right? So you're going to have two student objects here. And if you use P to change the name, those changes will not reflect on S.
Okay.
Okay, because you are assigning, because you didn't create a reference, you're making a copy. Okay, good question. Okay, so in Java, for example, when you instantiate an object, what you have is a reference, just like we see here, right? You don't need to do dereferencing. You just use the reference variable and you use the dot operator to refer to individual fields within that object. So a much safer mechanism to access those more complex structs or objects. Okay. So let's finish now talking about semantic analysis and attribute grammars. We're done with the slide 10. Let's look at slide 11. Okay, so this is a short introduction on semantic analysis, because I just wanted to be thorough on my introduction for you guys about all the phases of a compiler. You were able to look at the lexicon analyzer, syntax analyzer. You probably are much more confident now after you've been working on your programming assignment, right? understand those two phases, that the output of the syntax analyzer is the parse tree, right? You saw that, and that's one of the requirements for your programming assignments, to make sure that the parse tree looks exactly the same way, so the next phase, the interpreter, is able to run that code. But we haven't talked about much about the semantic process, right? So the syntax means whether you wrote the code correctly according to the programming language grammar, right? So you guys understand that. But what is semantic, right? So the semantic part basically will check some language rules that go beyond the grammar. So there are other things to check. They're not expressed in the programming language grammar. And this is what we need to talk about when we discuss semantic analysis. And also, during the semantic analysis phase, that's when variables are allocated to specific memory locations. So for example, we don't have in our programming assignment for the mouse programming language, we don't have a specific semantic analysis class because it's embedded in the interpreter. I put them all together. But when I'm creating that array to specify the memory addresses of each variable, controlling the value of each variable in a big 26 size array, I'm basically doing the binding between memory, between variables and storage location. Because I'm running a virtual interpreter, it's not basically, it's the program is the interpreter, right? It's like a virtual machine. I have the freedom to control how I'm going to structure the memory, right? I'm not mapping those variables to any operating system allocation, memory allocation process. I'm using a simple array because it's a virtual machine. So I define how I'm going to allocate memory. So I decided to use a static array. But that decision is part of the semantic analysis. So let's talk about some of the rules that we see in a semantic, that's part of the semantic phase of a compiler, right? Or defines the semantics of a programming language. A very common rule found in many programming languages says that variable needs to be declared before being used, right? So especially languages that are statically typed, right? You need to explicitly declare a variable before use, right? So that allows the compiler to check if the type you're using is the one you said when you declare the variable. So that's a common semantic rule. Why is this a semantic rule and not a static rule? Right? What you have in the grammar is that this is how you declare a variable. You need to specify a type, and you need to specify an identifier. That's how you declare a variable, right? And then later you're gonna have uses of that variable. For example, you have an assignment expression where you have a variable, a symbol, and then the value being assigned to the variable, right? But how can we check at some point that, oh, this variable is being used in this expression? Was this variable declared, right? So there's no way for the syntax analyzer to check that, right? It's something that needs to be done later. As the syntax analyzer is processing variable declarations, right? It needs to maintain what we call a symbol table. Whenever it sees a variable declaration, it needs to say, look, this variable x was declared as int, right? So later on, the semantic analyzer, when the semantic analyzer sees an expression that uses x, the semantic analyzer needs to go to the symbol table and check, what's x? What is x? X is an int. Does it make sense to have an int in that expression or not, right? So it checks those things. Or you have an assignment, let's say x was declared as an int, but in this expression, I'm assigning, let's say, a string to that variable, right? So later, this is another problem. Are the types compatible in an assignment expression? So that's a semantic rule that needs to be checked. Is the variable being used in scope, right? Okay, the variable was declared, but the variable is not visible in that specific scope, right? So scoping rules are also part of the semantic analysis. Type checking functions. So when you make a function call, are the types compatible, right? In the grammar, you just specify how a function is declared, right? And how a function is called. But can you check if the types are compatible when you make a function call, right? So you need to do those checkings, and those things are more complex and need to be done later in the compilation phase. Here's an example of semantic error in Java. You're trying to use X, but X was declared, so this is a typical semantic error. Another semantic error, you're trying to redefine a variable. This variable is already defined, right? So that's another semantic error. But if you look at this from the syntax analyzer point of view, can the syntax analyzer tell that this is a problem at the syntax analyzing phase? Doesn't this look syntactically correct? Those both expressions here, they're syntactically correct. So is this one. This is also syntactically correct. We just assigned the value 10 to x. But the fact that the variable wasn't declared, it's a violation of this semantic rule that is defined in the language. Here's an example of a function called semantic error. The way you declare this full method here, you're saying that, okay, it requires an int, it requires a string. But then when you call the function, this method foo, you're passing a string and an int. So you flipped. That's another semantic. It required int string, you pass a string int, right? And again, syntactically, this call is correct. You're having the function name inside parentheses, you have an enumeration of arguments, but the matching of the arguments in the parameters, they are incompatible, and the matching can't happen here, right? Here's another example, assignment with incompatible types. You're assigning on the right-hand side of the assignment, you have a string. On the left hand, you have an int. So that's incompatible. Also incompatible float to int. Okay. So what is hard when we start talking about semantic analysis is that how can you express rules? Okay. So think about, maybe you can talk to each other. How would you formally specify those rules that we mentioned in a way that you can write a program that automatically checks semantic rules? Okay. Why don't you talk to each other and discuss that? Okay. join here.
I'm joking.
I literally, I don't know what that is.
So the.
Well, what is?
It's a
Yeah.
attribute.
You guys ready to go?
If it sees
We
that,
understand using memory.
Abstract parameters.
Should be there.
a variable information, so let's call it int a equals 2. And let's say it's
Certain amount.
Yeah.
Find out.
and C equals
If X is already in
ABC.
memory, you can't.
I think the second
Like
one
another
would
one, say,
compare
it's in there.
data type to
Like for type check.
expected versus
Well,
actual.
what about the
Yes.
ID and string?
Type identifier equals expression or memory. It does look really good.
Yeah.
Type or expression.
So you're actually going to talk about like
You know, different
writing a
type.
program that looks for the grammar.
So it's just another syntax analyzer.
Grammar that.
Well, kind of, yeah, but it's like a key value pair.
I was gonna say hash maps has to be the answer.
I think I'm
So I think they might be switching to Java.
Everything is a map.
Which makes sense.
When I throw out everything. Say, okay, when I see something syntactically correct, like declaration, then I put that variable in declarations. And then every time it's called after that, as I'm reading through the program to verify,
also.
then if it's not in that map, then
Like function call.
it's fine. You can have all kinds of maps like that.
I think
Yeah.
you can just keep an eye on these variable types. So when you say calls, just make sure, hey, you have an int here.
So we decided that hash maps are always the answer.
Just so you actually in the first place. And then
Like if you have,
bonus points, right?
looks like
Yeah.
Like
Like if you have a hash map, for instance, that will take all of your declarations and every time you declare something, puts in the map, it puts also like maps in scope and stuff like that. So then every time you reference it after that, you can see if it's in the map.
So basically, you're gonna use a hash map. No job.
No job.
Yes.
Nobody.
Is that
So
bad?
basically,
Everything
what
looking
you
for,
do
yeah.
is you kind of maintain information about.
Does it work though? Because like with scope, that's where you run into problems. How does the,
Just create a column that says where.
You could try, like, as you enter a new scope, you add a new, like, scope level. And then, like, when you make the closing brackets or the, you know, whatever. right,
then you
it
change the
ends
scope
that.
level?
Then you basically, anything that's in the current scope level, you just delete from the table.
That works.
Keep the table always updated, yeah.
Right. So basically your semantic analyzer is gonna run line like through the whole file and update everything as it goes on. We went, see, hash maps was the answer, guys.
Okay, I hear you. So, it's not easy, right? It's not easy to figure that out, right? You guys over there, what are your thoughts? You're talking about using a hash map?
That's your idea, not mine.
Harrison explained it best, actually.
Sure, okay, so the idea is that you would essentially have something kind of akin to a symbol table, like you would track all the different like attributes of all your different symbols. So you might say like this is an like X is an integer, it was defined on line, or like I guess you just put it in there if it's defined, and then like whenever you run across a reference to something, you would check that table, and if the reference isn't in there, then you can just say this isn't defined. If it's being used as the wrong type, you can tell because you know what type it is, and then like scopes, like as you go into a scope, you like say, okay, well I was, in main, I'm at scope level 0, and then I go a function call, so now I'm at scope level 1, and I add everything in that function at scope level 1, and then like when the function call returns, I just go and delete everything I added at scope level 1 because it's no longer in scope. So you could handle like type checking and like declarations and scope stuff that way. I don't know if that would get everything though.
Yeah, you maintaining the symbol table, you just add attributes like if lifetime of the variable, right? Or the things you're defining, and maybe visible, right? To see if the variable is visible, is in scope or not, right?
Yeah, so we can use the same things that we already have and just add different attributes and remove those attributes?
Yeah, so you're talking about the specific that we have as in the programming assignment?
Yeah.
Yeah, so I don't think the syntax analyzer had a symbol table. I think it was something that is only in the interpreter, specifically on that assignment. But the general idea, you're right? You need to maintain a table of symbols, right? Any other ideas, any other comments about how to formally represent these rules? Right? It's something that is not easy because there isn't like a well-established standard, like we have the BNF, for example, for grammars. You don't have that for semantic analysis. So pretty much because essentially, because it's much harder to define rules formally. So the normal approach, and this is what we see more often, is to define rules using attribute grammars. So basically, think of attribute grammars as a grammar where you're going to add attributes to those variables that we have in the grammar variables. So the non-terminal symbols will have attributes. When those non-terminal symbols have attributes, we're going to say that this grammar is an attribute grammar. Those attributes are used when specifying semantic rules. So I'm just going to give you guys some examples of how an attribute grammar will look like. So let's see this simple example that shows an assignment grammar rule, basically saying an assignment is defined as a variable on one side, an equal symbol, the assignment operator, and another variable. So this is very specific. This grammar, you can't assign the result of an expression to a variable. You can only copy the value of a variable to another variable. So it's very limited as the first example. And a variable, just to keep things simple, can only be A, B, or C. Okay? Very simple. So we start with something very trivial. And the rule we want to add is that types of the variables, they must match. And assume that each variable has a type. Okay, so A has a type, B can have a different type, right? So the only rule that we want to check here is whether the types are the same. So this is how we're going to express that. The attributes are basically columns in the symbol table. So when you do dot type, we're basically doing checking the type associated with a variable. So the syntax rule is saying that an assignment is var. So we're going to add this index 1 because this is one variable, this is another potential, another variable. Okay. So the rule we want to check if is this one. The the variable on the left side, type, has to be the same, the type of the variable on the index 2 here. So the types must match, okay? And this is the third reference to the var symbol, so we're going to use index 3, and it can be A, B, and C. And in order to figure out the type of a variable, we're just going to do a lookup using the variable's name, and this lookup is basically going to the symbol table, okay? So whenever you see a lookup, it means go to the symbol table and try to figure out, using the variable's name, try to figure out its type. So let's put these things together. So lookup, search the symbol table for a variable's type. The name attribute has the name of the variable. Okay, so let's just go over this example. You have the parse tree here, and we have this example where var is A and the other variable is B. Okay, I guess we need the symbol table too. Okay, so let's pretend that the first lookup gave me the variable A here, the type is int. So we look up, and using the variable's name A, we found that the type is int. So all of these are attributes that we're going to assign to nodes in our parse tree. Remember our implementation of the project, it allows you to add attributes to nodes, right? That's how you add the value attributes for identifiers, right? And this was done in purpose to allow later us to represent semantic rules. You add attributes to your node in your parse tree. So now this other variable here, we do a lookup and we see that the type is int. And according to the rule, the types of this var and this var, left and right hand side, they are compatible. So the semantic rule checked. Things get more complicated when you have expressions, because we don't know the type of an expression until you evaluate the expression. And this can only be done at runtime, right? So when you have expressions, things become more complex, because how are we going to evaluate what is an expression, right? An expression, in this simple example, you're basically doing the addition of two variables. Because this is very simple, you don't have function calls or anything like that. A semantic rule using an if-else statement is sufficient. So if the var index 2 here, the first of the arithmetic expression, is equal to the index 3, the second value, that's fine. Or we try to figure out what is the expression type. So if they have the same, so the expression type will be either var2 or var3. Otherwise, we're gonna set the expression type to be float, because this grammar, I guess I need to add more explanation here, has only two types, int and float. If the types are different, so let's assume that the expression type is float. And again, we do lookup to get to the values. So we're running out of time. We're gonna discuss this again on Thursday. I just wanted to introduce today. All right. So thank you.
So what you do, if you cancel it now, look at that
For real, dude.
So, yeah, so just make sure. I guess all I have to say is make sure you cancel it, because that shit gets fixed.
Is it per month is 5?
Yeah, it said that, and then I got charged for 30 bucks.
What?
Sounds like they charge you like
Yeah.
an annual fee.
No, I don't know, man.
Yeah, kind of.
So less than 2.1.
What is it? CD, we're using the CD for the next one.
So after these, usually we're good.
Yeah.
So, yeah.
After.
Okay, yeah, that
Go home, and then, we can hop on and try. Sure. That's. Probably, yeah, and I can meet earlier, because, you know, I've got to get up. Wednesdays are really early. So, I can definitely meet earlier, and at least see where you got this afternoon. We can kind of find out any of the issues, because I think we're close. Yeah, yeah. I think we're close. Again, a couple of things that we need to. Exactly, and then all we gotta do is just write the little mouse program that just meets the conditions. And honestly, if everything clicks really easily, and then we can be like, oh, cool, let's do these extra credits, that's great. Yeah. But I'm not worrying about those right now. Yeah, yeah. I think that's the right approach, is like, just get everything else done, and if it's to the wire, then.
Figure out the type of the hole.
Because that way,
What's up?
the subtree that's over here or over there can throw an error before it even gets there, like, oh,
The
this isn't,
recursive
this
descent
isn't
pressure?
an integer, so.
For
They
syntax
have
analyzer?
this expression.
Yeah. Well, I mean, we just kind of, yeah, you broke it down the same way that you did
Now you
1987
have the type of this
with the, you look at the grammar, and parse, and then the first line, and then if there's a non-terminal, then you have a new function that parses that. So you get parse mouse, parse statement,
And you have enough information. to
parse
decide
string,
whether
parse
you
literal, all
like
that
it.
stuff, so it kind of like breaks down from there.
That's complicated.
It is.
But it's pretty cool.
As opposed to bottom up, I don't know. I assume